Hi everyone, and welcome to today's webinar, Engineering to Go. My name is Donna Long and I will be your host during today's webinar, presented by Zane Scott. As Vice President of Professional Services at Vitech, Zane Scott manages the company's consulting and training organization. For the past 25 years, Zane has built a skill set that enables him to provide insight and guidance to individuals and companies as they improve organizational processes and methodologies. Zane has also taught systems engineering methodology in a variety of settings, is a frequent blogger, and a co-author of Vitech's book, A Primer for Model-Based Systems Engineering. With a professional background in litigation, Zane is also a trained negotiator, labor management facilitator, and mediator. He has practiced tactical negotiation and interventional mediation and taught communications, conflict management, and leadership skills at both the university and the professional level. Before joining Vitech, Zane worked as a senior consultant and process analyst, assisting government and industry clients in implementing and managing organizational change. Before Zane gets started, I have a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Zane will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be available within the next business day. A recording will be published to Vitech's webinar archive located on our website. I will send the link out in the chat window now. At the conclusion of this webinar, a survey will open up on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Now I'm going to turn the presentation over to Zane. Welcome.
Thanks, Donna, and welcome everybody to our webinar this morning. We're going to talk about a topic this morning that I hope you find both interesting and useful, and that has to do with the portability of systems engineering. We're going to talk a little bit about systems engineering's origins and its focus up to this point, and what I think you'll find, as I do, an exciting expanded focus that's available to our discipline. So with that said, let's get started. Where are we going this morning? First, we're going to take a little bit of a look at our history as a discipline, how systems engineering grew and how it carved out the niche in which it sits today. Then we'll talk about a need to diversify that has been intensifying since I've been working particularly with Vitech in the last 9 years. I have seen an increasing need for diversification for us in terms of our economic opportunity and in terms of our impact on the world. So we'll talk a little bit about that, and then we'll talk about how we begin that journey. And as usual, the journey begins with small steps, and we'll talk about the small steps that can come from something that the creativity and cognitive people call reproductive thinking. We'll talk about taking bigger steps with productive thinking, and finally we'll wrap up with some ways that I feel like at least systems engineering can embrace some bold opportunities to shape our world. The origins of systems engineering. We can trace the term itself back to the late 1940s. We find some mention of it in Bell Labs in the late 1940s, early 1950s as systems engineering. The concepts are older than that, because as we moved from a world where things were complicated to a world where things became complex, we begin to see a greater and greater need for someone to be able to look at things from a systemic perspective. They needed to look at things from a problem systemic perspective and from a solution systemic perspective. So as this increase in complexity began to come on the scene, a response to that complexity was needed, and that response is going to eventually be labeled systems engineering. The first kind of complexity that we're familiar with is something that's called detail complexity. We have lots of parts. We have lots of pieces that go together. We have lots of relationships and ways that they can relate to each other. And that composes detail complexity. Now, this complexity is distinguished from what we had experienced throughout history as complicated problems or complicated solutions. In complicated problems or solutions, you find that the system is pretty deterministic. If you think of the workings of a watch, if you know the relationship of the radii of the gears in the watch and the number of teeth in the gears and their relative positions vis-a-vis interlocking with each other, you can take the turning of one particular gear in that works, and based on that predict the new positions of every other gear in the system. Because that's a complicated system, but it's very deterministic. When you get into the realm of complexity, you find, and we'll discuss the definition of systems in a little bit, but you find in a complex system that the elements work together to produce results which are not obtainable by the elements themselves. It goes beyond itself in producing results, and so it's not deterministic, and you wind up with feedback loops and different reactions, and you can't predict. It's not like pushing over the first domino and having the dominoes fall in order as they go. And so detail complexity is one way that you can get into this realm. The other way to get into the realm of complexity is dynamic complexity. And in dynamic complexity, you have lots of movement of the elements in relation to each other and lots of changing of the relationships among the elements, and that causes complexity, and it causes a wide variety of behaviors that might emerge from the system. All this necessitated a consolidation of knowledge. No longer were we free to simply look in narrow little slices, but we needed to have knowledge about the context in which the system lives, the context in which the problem lives, and the context in which the solution is going to live. We had to have knowledge about the problem itself. We needed knowledge about the way in which we were going to design a solution, and then finally, and very importantly, we needed knowledge of the solution. And all of this needed to be consolidated so that it could be viewed through a single lens. It needs to be viewed in a way that we can align our assumptions and our information and work in the direction of a solution that fits within the context and actually solves the problem. That was the genesis of systems engineering. When you put all that together, that's the disciplinary area that starts to be called systems engineering. One of the ways, the first ways, and I showed you the illustration on the previous slide and the illustration here, have to do with missiles, because this is one of the areas where systems engineering came right to the fore. We had a Cold War space race and a Cold War arms race, both of which turned around this new science of missiles as weapons, and missiles as offensive weapons, and missiles as defensive weapons. And so the marriage of the disciplines involved in producing these weaponized missiles or the rockets that went into space, that became a very complex space with a lot of disciplines playing together. So as you design propellants, be they solid propellants or liquid propellants, you had the chemistry people talking about the different conditions, temperatures at which the chemicals can combine and temperatures at which they'll perform. You have the people who design the propulsion system so that you don't just get an explosion, but you get a controlled explosion that's focused and moves the missile forward. Aerodynamics, how's this thing going to fly through the air? How's it going to fly in space? The orbital dynamics, once you begin to talk about putting missiles into orbit. There was all the science that went into the weapons. How could you pack a weapon into a missile as a payload? How do you guide the missile? How does the missile detect threats? How does it communicate with the ground? How does it find its target? All of those involve different engineering disciplines, from disciplines with computers, disciplines with communication. All these different disciplines had to be aligned. It was a whole different problem than designing a locomotive. You know, initially you have a locomotive that operates off of steam power. Your fuel is coal. You shovel the coal into the fire. If you want more steam pressure, you need to raise the temperature, so you shovel in more coal. But essentially, the locomotive design was a mechanical engineering problem and was pretty much confined to that domain. So these new problems with missile systems brought on the need for a new level of coordination and overview. Now, this had some interesting results. As systems engineering grew up and got a hold of all of that and began to consolidate it and use it to build the systems that were involved, it created a barrier to the world, because the processes, as the processes were defined, became tailored processes for the domain. So rather than taking an existing discipline with an existing set of processes and saying, what do we need to do to tailor those processes to this particular domain, the processes were homegrown in the domain area. So they became domain-specific process definitions. We wound up with lots of domain-specific language, both with vocabulary and usage. And while these facilitated the work that was going on in this new mil-aero space, if you will, it became a significant barrier to expanding what systems engineering could do in the rest of the world. So why do we care about that? Why do we care about that barrier? We've lived in this space. We work in the mil-aero space. We've made some small forays out into other areas. Why would we begin to care? If you notice the NCOSE Vision 2025 report, one of the emphasis in that report is that there's a much wider playing field for systems engineering than simply the traditional mil-aero spaces. Why does NCOSE care about that? Why do we, as practitioners and academics in the field, why do we care about that? Well, if you look at what's been going on in our market space, you see that there is some pressure to diversify so that we're not subject to the ups and downs in the marketplace. If we look at the market itself, we see that the nature of warfare is transforming itself. No longer do we have big Navy facing big Navy. where the number of carriers becomes critical, or the number of battleships, or the number of cruisers becomes critical. No longer do we have large armies facing each other on the field of battle. So the problem is changing. The problem set that we're facing is changing, and we're getting involved in something called asymmetric warfare. If you want to read an excellent book on how warfare is changing and how we need to adapt, I would highly recommend General Stanley McChrystal's Team of Teams. That gives you a good picture of how our mindsets have to change in order to allow us to be competitive and exert our material advantages on the field of battle and in the conflict landscape across the world. The other thing that's been going on at the same time is not only is the nature of warfare changing, but the funding stream is changing as well. The 2011 sequestration and the 2013 budget deal all constrict the funding from what we were used to in terms of growing defense funding. And so, for instance, in March, you had testimony when the budget request came out, and DOD had cut 24 Army UH-60 Blackhawks out of the budget, 5 Air Force F-35As, 5 Navy Ticonderoga cruisers, 77 Marine Corps Joint Light Tactical Vehicles, and $1.3 billion in military construction and certain critical nuclear modernization efforts. Even more importantly to us, that signals that the funds for developing weapons down the road from those which are production weapons, the funding for developing weapons beyond that has been slowed down significantly as well, which means that the pot of money is decreasing and the demand for the big complex systems that are based in products, in metal, in bending metal to make a variety of war-fighting machines, not only has that shrunk, but the development funds have shrunk as well. We see it in other areas of government. The astronaut with the for sale sign on the space shuttle and the contracting of those budgets and the cutting off of efforts like the space shuttle all mean that we have a diminishing market. We need to respond to that in some way, and the response is to look and see where are the new opportunities. Where can we actually be of service? Where can we A, earn our livings, and B, serve our country and our world with our discipline? This calls for some exploring, and what I'm submitting to you today is that I think that this exploration of new opportunities is a journey. It's a journey that begins with small steps, the small steps that come from reproductive thinking, and we'll talk about what that is. The steps that are larger that come from productive thinking, and we'll talk a little bit about two very critical areas that we need to pay attention to in order to get out of our traditional systems engineering box. So first, let's talk about reproductive thinking. What exactly is reproductive thinking? Well, with reproductive thinking, we focus on reproducing proven solutions. We focus on looking for areas where there are similar problems and areas where there are similar solutions that are being applied. So we naturally try to to figure out where our processes can best fit, and we do that on the supposition, and it's not an unwarranted supposition, that if you have like kinds of solutions being produced, then that may be an area where we have an opportunity to reproduce our solution. I will never ever forget one of the first talks that I gave to a group about the need to diversify. And I talked about the need to diversify and pitched lots of the ideas that you'll hear me pitch today. And at the end of it, one of the participants said, you know, I think you're right. I think we've been working on this tank, this fighting vehicle, and I think we could also probably produce bulldozers and other equipment. I thought, what's he talking about? And what he was talking about was he saw one tracked vehicle and another tracked vehicle. So if we can design fighting tracked vehicles, we could design dirt moving tracked vehicles. Now, that's not the largest innovative step in the whole wide world. But it's not an invalid step either, because it represents reproductive thinking, probably down at its lower limit, where we move from one tracked vehicle to another. But in reproductive thinking, we move from one kind of solution to a similar solution set and engage in that new opportunity, if you will. Now, a couple of examples about how this really happens. It goes beyond the one tracked vehicle to another concept. Let's take the example of some of the things that are going on in the oil and gas industry. And this is an area where systems engineering is currently growing. Oil and gas has a new NCOSE working group dedicated to advancing systems engineering in that industry. They're beginning to embrace systems engineering. And there's a serious engineering effort going on in a number of situations. I owe a heavy debt here in talking about this solution to a paper that was presented at the International NCOSE Symposium in Scotland this summer called Systems Architecting for a Retrofittable Subsea System Application. That was produced by Jason Baker and a number of his colleagues at Transocean, talking about their journey toward introducing a disciplined, robust, model-based systems engineering effort to solve oil and gas problems within their industry space. They face an interesting problem. As you begin to drill, you go from drilling in the situation where you're drilling in your backyard with discoveries of oil reserves that are available to you in your own country, on your own continent, etc., to move offshore and move into deeper and deeper waters and move worldwide into drilling undersea worldwide. And their paper focused largely on the undersea drilling. You're talking about, and this is fantastic if you're not familiar with what's going on, you're talking about drilling 1 mile to 3 miles under the surface of the water. So some of the issues that they face are the operational setting, all of the contingencies that go into going down 3 miles to the ocean floor and then drilling under the ocean floor to try to recover the resources that are down there subsurface. So you're not just drilling, you're not just working 3 miles down, but you're working 3 miles down plus your drilling distance down. So your wellhead may be 5 to 15,000 feet below the surface, below your drilling platform. So the operational setting is challenging. If you're going to do this in a global way, you find that the jurisdictions scattered around the globe all have different rules, and you've got to follow the regulations. You have to live within the regulatory environment. So as you're designing solutions for this undersea drilling, you have to take into consideration the fact that this has got to be easily fitted for working in multiple global jurisdictions and for compliance with a number of regulations. Secondly, it's the old problem that we have found in systems engineering, where we're not always invited to the party where the customer is saying, okay, design me something brand new. Let's just clean slate this. Instead, what you're trying to do is you're trying to solve problems by retrofitting solutions into equipment that already exists. And you won't find an oil company who can scrap the oil platforms and just say, start over again. We'll design this any way you want, or scrap any of the rest of their solutions. You've got to very carefully solve problems by retrofitting equipment. And then you have to have performance that justifies economically your venture into it, and performs in accordance with all of the requirements and regulations that are imposed on that situation. Well, this paper detailed how they brought in a full tailored MBSE approach and began to work top down to engineer to the new performance requirements, and bottom up with the existing system and the existing issues to arrive at a solution. And they tell the story about their journey in doing that and about how they had success. This is a good example of taking a solution that has been applied, not the undersea solution, but the solution of implementing top-down and bottom-up in order to provide retrofit solutions into an existing system, and moving it over into a domain where it hasn't been used before, and adapting and tailoring the principles and the approach so that you get successful solutions there. This is reproductive thinking at its very best. This is making us a step to a field of new opportunity where we haven't really played before, and doing it in a way that is very, very successful. Another area where we see the reproductive thinking at work is in the area of healthcare. Now, Nkosi started an initiative among several other industries with the healthcare industry, and basically said we need to be able to move into healthcare. There are opportunities in healthcare, and we could do these systems engineering solution systems and find new opportunity there and be of great service to that industry. Well, the first thing that they seized upon when they moved into healthcare was healthcare devices. Well, why devices and not delivery? Why were devices the first place to go? Because we have a natural tendency toward the reproductive thinking. The most obvious opportunity is an opportunity that's born of a solution that looks familiar. So if we can do control systems for aircraft, we ought to be able to do control systems for operating rooms. If we can make highly technical devices in the mil-aero space, we ought to be able to make highly technical devices in the medical space. So medical devices was a natural avenue to go down. And we began to look at control systems, hardware, infusion pumps, and implantable devices. All of these areas are familiar in the sense of the same kinds of problems that we had solved in other settings. And they had a need for systems engineering because they're highly regulated, they have complex requirements, and they have critical tolerances and critical performance standards. Let's look at one. The area of defibrillation technology. This is an interesting area. I might say today that it's near and dear to my heart since I have one of these devices that is the implanted kind. But medicine has long known that you could restart the heart when it stops for a variety of reasons. You can restart it with an electrical stimulus that passes through the atrium or the ventricles. So you wind up with external devices that are designed to pass that electrical current through the heart and stimulate the heart into its regular beat pattern. The device on the left is such an external defibrillator. This is actually much smaller than the original ones. This is a device that you might find sitting on a cart or hanging on a wall. And the way this is used is that one of those pads is applied to the front and one of those pads is applied to the back, and they're basically aimed so that when they're fired, the electrical current will go from one pad to the other, passing through the heart and restarting the rhythm. Well, through some superb engineering and technology, they discovered that they could implant a device that could be hooked actually into the heart muscle, through the veins, down into the heart muscle, and provide the electrical stimulus directly into the muscle through a battery and a generator that generates the stimulus. Reduce the size of all of that so that it became implantable. The initial ones that were implanted were rather large. You could tell if somebody had one implanted by looking at their chest. There was a big lump. Now those devices are down to what you might, for comparison, think of a stack of silver dollars, 3 or 4 silver dollars glued together in a stack. That's about the size of an implantable defibrillator pacemaker today. All of that requires very critical engineering because there are a number of issues that you have to deal with as you do this design. There's risk to the patient. Initially, some of the implantable devices had problems with reading the information from the heartbeat that it was receiving and misinterpreting a natural process going on as a bad process and repeatedly shocking the patient. And that's no good. You don't want this device inside your chest shocking you till the battery runs out. So that was one of the performance standards. The other side of that coin is that if your heart does indeed stop or get into a fatal rhythm pattern, you do want it to deliver the electrical therapy to get you straightened back out. So there was a good deal of patient risk. The stakes are high because this is literally a matter of life and death. As you might imagine, with devices that are going to be implanted in the human body, there are numbers of regulations, an extensive regulatory environment that has to be complied with, both applying to the process of developing these devices as well as to the devices themselves. There were design considerations. What's the life of this thing? How long can the battery last? Interestingly enough, now they have these devices that can last 10, 12 years before they have to be replaced, because every time you replace one, you have to open up the patient and actually pull the device out and exchange it for a new device in order to get the new battery life. And anytime you do that kind of an invasive procedure, you bring on a whole set of risks. So you want that to happen as few times as possible across the life of the patient. It needs to be miniature. Those of us who are old enough probably remember the first artificial heart that was implanted in someone, and how big that was and how big all of the external devices were. This has to be made miniature so that it causes as little problem as possible for the patient. And then you have to develop a monitoring system. And so all of that needs to be engineered. As a matter of interest, the device that I have now has a monitoring station which will sense the information stored in the device implanted in my chest, dial through to a cell tower, its own cell tower, not even through my cell phone, but it'll hit a cell tower and it'll upload the information from my device to the doctor. So the doctor can take a look and tell what's going on with my heart based on the information coming from that device. All of that brought to being by the engineering behind it. And somebody has to be looking at that engineering from a systemic perspective. That's the job of the systems engineer. So there are opportunities out there, and these are reproductive thinking kinds of ways of approaching those opportunities. Now, how do we open up the box and move to productive thinking? Well, productive thinking first involves the similarity of the concepts behind the processes of the engineering, whereas the reproductive thinking focused on the similarity of the solutions and the approaches to the solution. Productive thinking involves understanding the concepts behind systems engineering and looking for places where the problems look like problems that are susceptible to the application of those concepts. So the first place that we turn with productive thinking about systems engineering is to the systems definition itself. So recall that in the NCOSE definition has these three prongs, and almost any definition that you can dig up of a system will have these three elements in common. First thing is that a system is made up of different elements. The second is that they are arranged in a construct. In other words, the elements are arranged in relationship to each other in a particular way. And then finally, and the bottom line on systems is that they produce results beyond those that could be expected from the elements alone. So different elements arranged in a construct that produce results beyond those that we could expect from those elements alone. Now, those are the concepts that we need to understand, and then we need to look at the problem space and say, is this a problem space that could benefit from the application of those concepts? We can also understand the concepts by turning to the other areas of systems thinking. There are a number of systems disciplines: systems thinking, systems theory, systems science, and the emerging disciplines of complexity theory and chaos theory. All of those will give us pathways that we can use to think about problems and look for the similarities in the problem structures. That involves a change in the way that we think. So we engage in productive thinking rather than reproductive thinking. And then the next thing that we have to do is we have to change our language. Now, remember when we talked about the origins of systems engineering, we talked about how it was domain specific. It grew up as domain specific. The software engineering community has had a great influence on us, and now we have an infusion of software engineering terms and software engineering concepts that are also very much domain specific. I'll never forget one of the first sources of confusion for me when I came into this particular technical area was the use of the word agnostic. Now, I knew the term agnostic. I knew that it came from the Greek word gnosis, G-N-O-S-I-S, which means knowledge, and the prefix a applied to gnosis means without knowledge. So, for instance, in the world of theology, somebody who is a theological agnostic does not say, yes, there is a God, or no, there is not a God. They say, I don't know whether there is a God or not. In other words, I'm without knowledge. I came into this area, excuse me, and began to encounter software engineers who would, it seemed to me, boast that their applications were operating system agnostic. And that caused me to wonder, why would it be a good thing? Why would you want to emphasize that your program operates without a clue as to what the operating system is, without any knowledge? What they actually meant was that it didn't care what operating system it operated under. It worked equally well among a variety of operating systems. So operating systems were not a source of concern for it. We won't get into it, but there's a perfectly good Greek based word that applies in that situation. But they were using the term agnostic in a way that caused me confusion, at least, until I learned what they actually meant. Now, domain to domain, we'll find that to some extent or another, each domain has its own language and its own usage. So, if we expect to have an impact, to convince people within new domains that we have something to offer, something to bring to the table, we need to do two things. We need to, as we just finished discussing, we need to understand our discipline at the conceptual level beyond the specific application level. So we need to understand systems engineering processes in terms of the fundamental concepts. And then we need to be able to take the systems engineering language and think of it in terms of the domain neutral concept descriptions. So rather than using the words requirements in a particularly narrow sense, we need to find a way to talk about the purpose and the mission. We need to get outside of the narrow definitions that we give those terms and others, and to think about what language will resonate. And then we need to go and do some learning about the new domain. We need to understand the new domain and understand that the new domain has its own language. So we become able to translate, we become able to speak the new domain. But to the greatest extent possible, we need to be able to speak in domain neutral language so that our solutions are as transportable as we can possibly make them. So what do we do to get systems engineering to go? I had to laugh as I was preparing this. One of my reviewers thought that this was systems engineering tied to a ceiling fan. Actually, this is systems engineering being delivered by a drone. In other words, advancing ourselves as much as we possibly can. So how do we do that? Well, as we've said, we need to learn conceptual level thinking. We need to ask ourselves what problems are being solved in the target domain. Are systems involved in those problems? Are they involved in the problems themselves? Will the solutions be systemic solutions? We need to look for analogous concepts between the domains and for ways of talking about that. We need to learn the language and the concepts of the new domains, and we need to use domain neutral language wherever possible. So we need to speak in terms of concepts. One of the keys to learning the concepts and learning to speak of the concepts in domain neutral terms is to go to some of the other systems disciplines. If we spend some time in the area of systems science or spend some time in the area of systems thinking, if we look at complexity theory, if we look at chaos theory, then we begin to pick up on the ways in which the language is explained in and I don't mean to say non-technical, because some of their language can get pretty technical in terms of their own domains, but non-domain specific, if you will. So we need to learn how to think about the concepts and how to talk about the concepts in ways that are not domain specific and that we can translate depending upon where we need to talk and present. So what kinds of possibilities are there out there? What sorts of things can we get involved in? Two areas that come to mind, because these are areas that are kind of on the cusp of what we're doing, is we can begin to think about healthcare delivery. How does an operating system, operating room operate? How does that system operate? How are we sure we have the things we need? How do we cope with the situations that may arise? How are the resources put together? How do we get information about what's going on to the people who need the information? How is all that coordinated? So not just the infusion pump next to the bed, but the broader scope of the delivery. And then open that up and say, okay, so how does the hospital operate? And open that up and say, how do we deliver health care in this particular setting? All those can be, and some of those are already, systems engineering problems. But they all represent opportunity. And they're opportunities for systems engineers who are looking for ways in which they can provide useful solutions. Another area is disaster relief, whether you're talking about flood, earthquake, getting resources, rebuilding, doing construction, those kinds of things, to medical disaster relief. How do you position your resources around the world so that you're able to pounce if we have an Ebola virus breakout? Or how do we respond to particular epidemics across the world? Those are systems engineering problems. If you think about them, the problems live in a systems context, and any solution that is delivered needs to be delivered in a systems context as well. And who better to do that than systems engineers? So where have we been? We saw how history shaped our development in domain-specific ways. Our processes, our language are all domain-specific. We feel the world around us telling us that we need to diversify. We need to serve in other ways. We can take small steps in terms of reproductive thinking. These are not tremendously uncomfortable and are eminently able to be accomplished. We can take bigger steps using productive thinking. We can understand at the concept level. We can communicate at the concept level. We can develop non-domain specific ways of talking about things. And in doing so, we can find real important opportunities that can actually shape our world. So I hope that you're as interested in this diversification effort as I am, and find it as exciting as I do. And I appreciate your time and attention today in being with us, and it's good to have been with you again.
Thank you, Zane. That was very interesting. We do have some questions, so if everybody, that's the end of our formal presentation, so we'll move on to the question part. If you have any questions, please go ahead and send that out through the questions tab. The first question is from Christopher. How would you respond to the view that any system that is designed is, in fact, deterministic and therefore complicated? Instead, complexity comes from when we put our design system into an environment where the users start to use it in a way that was never designed for.
That is a source of complexity, but design systems are not deterministic. I'm trying to think of a good example. Take the stock market. You could have, say, the commodities trading organizations that set up an exchange and provide ways for people to make exchanges. What happens with those, used in the ways that they're intended to be used, is that those markets will learn. The language in complexity theory is agents. They're complex adaptive systems. You can design an organization to perform particular tasks, and as the organization operates, it starts to learn things as a result of its experiences, and it will adapt. And so, particularly with complex adaptive systems, which can be design systems, you don't need someone out there using it in a way that was never intended in order to introduce complexity.
Okay, and Christopher had another question. If we accept that human behavior is difficult to predict, are you aware of cases where systems engineers are using behavioral psychology and probability to help with system design?
I'm not familiar with specifically systems engineers using that, but of course in terms of organizational psychology, and especially the cognitive branches of that, that's exactly what's going on. So I subscribe, and maybe I ought not to reveal this at this point, but I subscribe to the theory that there are a lot of systems engineers out there who, A, don't know that they're systems engineers, and B, have never heard the term systems engineering. And I think some of the organizational design folks are exactly that. And I think you could find cases of that among them.
Okay, let's move on. A couple people have had this same thought, so I'm going to try and consolidate a couple questions into their non-traditional system engineering parts or practices don't know that they need systems engineering, or they think they can do it themselves, it's easy enough. So what is the level of difficulty of expanding into these new industries, and what would be the costs and organizational restructuring that would have to occur?
Okay, I think that there are some costs. I think first, the biggest thing is the paradigm shift that we have to make in our own thinking, in our own ways of looking at things. You're exactly right that people in another domain are not going to necessarily greet you with open arms. In terms of, if you knock on the door and say, I'm a systems engineer and I'm here to help you, and I know nobody would be that blatant, but that's going to bring an allergic reaction. And sometimes when you present systems engineering, you will get the reaction of, this is so easy I could do it myself. Actually, if it were that easy, they would have already thought of it and be doing it themselves. So the need for the approach, I think, speaks for itself. But the way to approach folks like that is to look at their pain points, look at what's bothering them actually, where they'd like to be better, and talk to them in non-domain specific. Don't lead with requirements are the basis of functions which are performed by components. Don't go that direction. Go the other direction of saying, let's talk about ways that we might solve the problem. So I think it's a matter of A, changing our thinking, and then B, gently changing the thinking of our customer.
Okay, thank you, Zane. So I do have a question from Jamie. What is the difference between reproductive thinking and productive thinking?
You could boil that difference down to say that reproductive thinking focuses on the similarity of solutions, whereas productive thinking focuses on the similarities of the problems.
Okay. Well, let's see. I think we've answered all the questions. I'm waiting to see if anybody has any more that are going to come in at the last minute. But thank you so much for coming today. Our next, the next thing that will pop up will be a survey. If you could fill that out, I would appreciate that. Give us information on how this went and what other topics you'd like to see. Other than that, that's all for today. Once again, thank you for joining us and have a wonderful day.
Thanks, everybody.